conference from South Korea and share with us the result of his research. So for those who join us for the first time, there is a series of talks where R&D experts and the people who are keen to share their knowledge in R&D had a presentation and sharing technology trends and insights where those technologies might be implemented in practice. Today's topic will be around AI, but not on those that are in the cloud, but about this that is run in the edge, especially at CFU. And you will know how you can cut the cost while making production use case more accessible and improve the inference of such AI models at the edge. So let me introduce you to today's speaker, Pavlo Hilei. Pavlo Hilei is R&D engineer who is focusing on optimization of AI and other algorithms on a big scale on the clusters that is also called high-performance computing. And today, he'll share us the knowledge within this domain and on the one specific example. Pavlo, the stage is yours.
Thank you, Dan. Okay, so let me share my screen. So let me know if you see. All right, so hello again. My name is Pavlo Hilei and I work at SoftServe R&D. And today I will talk about acceleration of AI model inference with custom hardware accelerator on the edge system. So this project is basically a continuation of my bachelor thesis, and it continued as a paper that was accepted on ICAP's 2024 conference that I just returned from, and more on that at the end. Okay. Here you can find an agenda for today's talk. First, I will introduce you to the problem we want to solve and how we want to solve it. Then we'll show you the tools we use for experiments. After that, I will show you the model we developed to solve our problem and software optimizations we conducted to achieve better performance. And finally, I will explain how I developed a hardware accelerator that to achieve a very good speed up, and then some conclusions. Okay, so let's start with introduction to the problem I solved and how I solved it. Okay, so basically, edge computing could benefit many artificial intelligence applications compared to centralized solutions. Processing data closer to its source reduces latency, improves responsiveness. It can allow more real-time use cases. It can minimize data transmission costs and potentially enhance data privacy. However, achieving acceptable performance within typical edge device computational power limits is very challenging. So when it comes to accelerator, there are various technologies. Probably the most popular are GPUs, CPUs. Also, sometimes people use FPGAs and ASICs. So each of this technology possesses some advantages and also some limitations. So I used FPGA for this in this project for development, since design can be easily reconfigured, and also FPGA allows quick and cheap development and testing. And FPGA solution also has potential to relatively painlessly be converted to the more energy and cost-efficient ASIC in the future. So in this work, I experimented with developing and implementing a custom hardware accelerator tailored for neural network on edge system. So the approach is a system with a RISC-V CPU, which is augmented by a custom function unit, CFU. So I designed convolutional neural network CNN model to solve automatic modulation recognition problem. And then I profiled this model, found some bottlenecks, and developed a model-aware accelerator to speed up execution of revealed bottlenecks. So the central part of the solution is the custom function unit. The main benefit of RISC-V CPU is that it is an open instruction set architecture. So it allows to any kind of changes we can only imagine. And one of such is extension is custom function unit. So on the slide, you can see overview of custom function unit. So basically, this is a custom piece of hardware that can communicate with CPU. And from the RISC-V CPU perspective, this is just a custom air format instruction extension. So we use this instruction, and when CPU calls this instruction, it sends some data to the hardware. Yeah, you can see the overview of how air format instruction for 32-bit RISC-V CPU looks. And on the right, you can see the CFU timing diagram. So without getting into much details, so this is basically a two-way handshake communication. Yeah. Okay, so now let's talk a little more in details about which technologies are used to implement such accelerator. So TensorFlow framework was used for model training and evaluation, and final model is converted to TensorFlow Lite Micro format. So TensorFlow Lite Micro is a version of TensorFlow Lite tailored for microcontrollers and other embedded systems that are constrained by memory and computational capabilities. It is shipped as a source code, and that makes it extremely easy to modify model layers to enable custom accelerator usage. Also, it makes it easy to compile each layer to find the bottlenecks, so find the parts of the code that takes most of execution time. We compile the code with GCC compiler for RISC-V. And as mentioned before, RISC-V instruction set architecture is very convenient for such applications since it's open and has many unofficial extensions such as CFU. And VEX RISC-V is one of many soft cores that implement RISC-V architecture, and it supports CFU extension. And it itself is implemented in LiteX framework used for SOX implementation. And finally, CFU itself is implemented in a system Verilog hardware design language. So Xilinx A700T board was used for experiments. So synthesization and of the design is conducted in Xilinx Vivado toolchain. So even though FPGA allows quite quick experiments with designs, it still requires quite some time to synthesize a solution. So using simulation can speed up development process a lot. And I used Renault to simulate CPU, and very later to simulate CFU. And all these tools are integrated in CFU Playground project by Google. Okay, now that we know which tools basically we use to develop, deploy, optimize, and accelerate model, let's get into more details and check out which model we trained. So yeah, problem solved is automatic modulation recognition. So in other words, this is a classification of modulation used for wireless communication. Signal modulation is, in a few words, is a process of modifying signal to enable it to carry information from one point to another. And in wireless communication system modulation, in wireless communication systems, modulation encodes information onto a carrier wave that are basically electromagnetic waves. And so modulation can be analog and digital, and this is determined by the type of information transmitted. You can see a visualization of amplitude shift keying modulation on the image on the right to understand what is modulation. So application for this problem can be found in cognitive radio, wireless network planning, and probably the most interesting application that also require near real-time performance is electronic warfare. So used RadioMel 2016.10b dataset. So this is a synthetically generated data set with GNU radio. It has 10 modulations and a lot of different impairments, such as flat Gaussian noise, timing, sample rate, carrier frequency offsets, phase differences, multipass fading, and so on. Yeah, and input data for model. So it has a shape of 128 by 2, where 2 is in phase and quadrature components of signal, and it is interpreted as channels of input tensor, and 128 is number of samples, and this is interpreted as a size of one-dimensional tensor. Okay, and so first model is CNN. So it is extensively used in literature to solve this problem, and it is good for signal processing like that, because CNNs can learn some hierarchical representation of data, find some relatively complex patterns, and feature some level of shift invariance. And you can see the model architecture overview on the slide. So this is very small and fairly simple in classic CNN. So it has convolution, max pooling, also fully connected with max at the end for classification, and activation function is relu. So we did quite a lot of fine tuning to get the best performance complexity trade-off. So like model width, model depth, size of kernels, and some other parameters are tuned. Yeah, also you can see a confusion matrix that visualizes a per class accuracy of CNN model. So if you look closely, it doesn't look very great, but you have to keep in mind that half of the data set has signal to noise ratio less than 0 decibels, and it comes up to -20. So it's very, very noisy data. Okay. So additionally, we also tried an encoder-based model. So we used classic encoder layers, which is multi-head attention followed by fully connected. And also one convolution layer at the beginning was fully connected at the end with softmax for classification. In such model, it's not required to use positional embedding, since wireless data should already encode positional data implicitly. And similarly, like we try to fine-tune all parameters possible in the model to get the best performance to size trade-off. And yeah, you can see the achieved accuracy for models on the table on the left, and signal to noise ratio in decibels to the accuracy on the plot on the right. So which shows that the better is signal to noise ratio, obviously the better would be classification. And so encoder works a little better for this problem, as you can see on the table, but unfortunately it's very slow. Even though it has less number of parameters, it's like 10 times slower than CNN. So that's why it actually makes sense to go with CNN to deploy it and accelerate it. Also, CNN is much easier to accelerate, since this is really a simpler model, and the final model has accuracy of 91.2% for a signal to noise ratio bigger than 0. Also, we use a full integer quantization, which gives a huge speed up, and we will talk about it later. But it eats around 1% of accuracy from the model, which is a good trade-off, as you will see later. Okay, so now that we have model, we quantized it, we deployed it. Finally, we can start with hardware acceleration. Okay, so as mentioned already, TensorFlow Micro is open source project, and so it's easy to profile code to find bottlenecks, and it's easy to see on the table on the left that a convolution layer takes majority of the time. So it really makes sense to accelerate convolution. Also, yeah, so model quantization has massive effect. As I already mentioned, it's approximately 7.2 times in our experiments. Plus, since we optimize for a specific model that has specific sizes of different parameters, and we can actually do additional software optimizations, such as, for example, some loop unrollings, hard coding some parameters, removing some cycle for cycles, and so on. So this can get additional 45% speed up. So a custom function unit itself does not restrict hardware design. So the main limiting factor is FPGA resources. You can see available resources of board used for experiments on the table on the right. However, unfortunately, CFU cannot access CPU memory, and there's no efficient way to transfer data. So we have to copy it manually to the buffer that is accessible by the CFU. So as we saw earlier, basically the interface is two 32-bit inputs, 10 bits to encode operation, and 32 bits to output. So the best solution in case of this board is to use block RAM, VRAM. So this is a RAM that is directly on the FPGA, and it allows 1 clock edge delay for access, memory access, and there's much more of this memory than, for example, what you can synthesize from LUTs or flip-flops on the FPGA. Also, if you think about it, convolution is basically a lot of multiply and accumulate operations, and they are very effectively implemented with DSP blocks. Yeah. Okay, so on this slide, you can see a simple diagram that visualizes accelerator design. So the main idea basically is to rewrite convolution partially in the hardware, a one-dimensional convolution. And so there are two buffers, input and filter. And each next computed value for 1D convolution is just per element multiplication, a sum of per element multiplication of input slice with filter buffers. So, and to use less memory, input buffer can be a ring buffer, since like you can visualize that filter buffer moves with the step of a stride over input buffer when you compute values. And the stride, for example, is 1 for this model. So this means that all but one row can be reused for the next convolution step. So you have to copy only one new row and move just pointer to the new to the start of input buffer, and in such way you can save a lot of memory. So configuration is saved to the register file. It has different values. For example, for quantization, you have to know the activation mean, activation max, offset, also unit bias for convolution, output multiplier, and so on. And so the main computation step consists of two switching states. First, we fetch n values from input and filter buffers, then we accumulate them, accumulate them, and update addresses of input and filter pointer. This n is multiply accumulate per cycle, and this is configurable parameter, and we will discover its effect on performance a bit later. Sorry. The next step is to quantize result. So inputs and weights of quantized model all are fit in 8 bits, and but when you accumulate results, it will grow much bigger. So you have to put it back into 8 bits. Okay, and also there are some other optimizations that help to get a considerably better performance. For example, quantized model works with 8-bit integers, as I just said. But since CFU interface has 32-bit inputs, we can actually copy 4 values at a time. And in this way, we can basically speed up copying by a factor of 4. Additionally, we can asynchronously copy values to the input buffer while CFU is still computing. So we can hide a copy latency a little bit in such way. Yeah. Also, we can actually make input non-ring. So this will make design much simpler and also quite quicker, but unfortunately the memory consumption will explode and it won't be as flexible, so it won't scale as well as a model, for example. Okay, so all changes are done iteratively. So more on which feature is introduced at which step is in the paper, but basically in version 2, we add a quantization module. In version 3, we copy 4 values at a time. Version 4 is some optimizations of the design itself to achieve better, higher clock frequency and to achieve better wall time. So version 5 is asynchronous data copying, and version 6 is removing of ring buffer. And you can see results. So when you do quantization plus purely software optimizations, we get 10.3 times speed up. Next is so version 5 with 16 multiply accumulate per clock cycle accelerates the convolution itself in 16.8 times and the overall inference of the model by 14 times. And overall, with software plus hardware optimization, gives 144.4 times speed up. And inference time is reduced from 7.5 seconds to 65 milliseconds. And version 6 results will be a bit later. But you can see already that a relatively simple design can achieve very huge acceleration. On the figure on the left, you can see how like different versions in different optimizations gave better and better speed. So on the y-axis is cycles of CPU, and on the x-axis is a version of CFU. And this x number is just how many multiply accumulate per clock cycle, and it is by default 8. And figure on the right visualizes how multiply accumulate per clock cycle influences performance. So you can see that you get better and better performance, but you start to use more and more resources of FPGA. And also this performance doesn't scale quite linearly, since we still have to copy data to the CFU. So it adds some constant time overhead. And it has version 5 and version 6. So we can see that version 6 is approximately 40% quicker, but it requires 8.5 times more memory for this model. So it's like trade-off. You want more speed, you have to give more resources, basically. Yeah. And so finally, let's sum up all work done in this project. And so yeah, we propose a flexible approach for hardware acceleration of deep learning models for edge system, which is based on custom function unit extension for RISC-V processor. And we tested this on FPGA. So first we train and evaluate a model. So this is so we decided to go with CNN model for our problem, which is modulation and recognition. And then we deploy this model as TensorFlow Lite micro model on a RISC-V CPU. Then we profile it, we found bottlenecks and decide which we want to accelerate with hardware. And finally, we designed this accelerator. So the one that we designed, version 5, gives additional 14 times acceleration, and version 6, 20 times acceleration. Plus with quantization and software optimizations, we also get 10.3 times inference time speed up. Yeah, but as I already mentioned, even though V6 is quite quicker, it requires much more memory. So for version 5, overall speed up is almost 150. Okay. So, and when it comes to future work, so there are a ton of things that can be done next. And for example, current design can be improved in terms of resource usages and higher frequency. And it would be very interesting to try to generalize this solution, for example, for n-dimensional convolution, and to measure the impact of this generalization in performance. we can deploy and accelerate other kinds of models and for other kinds of problems. For example, transformers architecture, they prove to work for many different problems, including the one that I solved in this work. So this will be also very interesting. And CFU extension can be extended to allow it to access CPU memory, and that should actually improve performance quite a lot and to give some flexibility to the accelerator. And also it will be interesting to convert the solution to ASIC and to verify if we can achieve, for example, some real-time constraints, real-time performance for some applications. Okay, so as I mentioned at the very beginning, this paper was accepted at the ICASP 2024, which is International Conference on Acoustic Speech and Signal Processing. So yeah, amazing experience, a lot of interesting people, events. And so ICASP actually considered it to be a very good conference. So it has, especially in signal processing, it has impact factor of 16. So 2,800 papers were accepted. And acceptance rate was a little more than 40%. And more than 4,400 people visited this conference. Yeah, and on this image, I am presenting the paper. Okay, so yeah, the paper is on the IEEE Explore Digital Library. And yeah, so in SoftServe, in R&D, we actively develop our HPC team and continue to look for new technologies to achieve high performance objectives for all kinds of problems. And that's it from our side.
Thank you for your presentation, Pavlo. Really detailed, really clear, speed up. So basically 12 times, and the numbers you show is like I believe may significantly improve some of the use cases we might work with our customers. I'm not talking about the past codes that you may achieve once you implement it for some of the use cases in production, but basically it will be really interesting to see also how it can be generalized, as you mentioned, for LLMs. We have one question for Yaroslav, who was an active listener. I want to check the research paper. So if you can share the link also in the chat, and we'll share it in the workplace. So the people will have it, will be able to like open and read it easier than that. But basically we include the link into the follow-up of this session. And yes, so if you have any more ideas based on the research you just heard, or any more questions that you want to address to the Pavlo, feel free to do it after the session. Neither you can send him on the email, or just like write down if you are part of SoftServe teams. And that's it. We were pretty quick this time, but still pretty focused. So if there are no questions for now, Pavlo, really thank you. Thank you for showing this for our listeners today. And for everyone who was here with us, I encourage to join next time. Also, if you have some topics or trends that you would love to discover, I encourage you to share them, and we can consider it as one of the future topics. And see you next time.